My name is Gary Dusbabek, and I work at Rackspace primarily on their cloud monitoring team, but we do lots of other different things. I have a good deal of experience with Cassandra. For a couple years, I was a pretty active committer, and so I come from that background. I know what's going on inside. I still like to think of it as just a big, long column store, which is different than it probably appears today. But that's the background I come from, and that's how I use Cassandra. I primarily just use it now as a developer. I don't get to have a lot of time to hack on it. What I'm going to talk about today is some software that we created at Rackspace to help us monitor our time series data. We generate a lot of it, and we want to be able to do useful and interesting things with it. And so that's what this presentation is about. I'm going to spend some time talking about why we created Blueflood in the first place, and then spend the bulk of this presentation talking about the guts that are on the inside. The design decisions that we made, why we did things this way or that way, and hopefully if you can, if you understand that, then you'll understand why the system is the way it is. And then I'll talk about some of the things that we're working on. This is open source software, and we're pushing it forward. We're doing some fairly interesting things that I think you'll want to hear about. So why we did it? There's probably three important things that Blueflood does, or that were important for us. The most important thing was to get the data in so that we actually have it somewhere. We don't have to worry about it going away. With cloud monitoring, we have these checks, and they generate, sometimes a few metrics, sometimes a lot of metrics apiece, and this happens in multiple data centers. And so, the example up there is each check generates between 2 and 20 metrics, but then each check gets executed in up to 5 data centers, usually about 3. We generate a fair amount of data that comes in. And for the longest time, we were just throwing it away. We knew that we wanted to be able to do some useful and interesting things with that, but we're a pretty small team as far as Rackspace development goes, and so we had to put this off for later, and that's what Blueflood is that later part that we're finally getting to realize. Some examples of what that looks like is if you use Rackspace, you can log into your control panel, and if you have monitoring turned on, the graphs that you see there are actually generated from data collected by Blueflood. Currently, we're ingesting about 120 million metrics per hour, which by Cassandra standards I think is still pretty small. Our production cluster is only 32 nodes, and we're not really even making it sweat a little bit. This ends up being about 40 million aggregate Cassandra operation or writes per hour. And so still, we're not really stressing Cassandra there. We have quite a bit of room to grow into. So we're impressed and happy with what we see so far, and we know that this system is going to be able to hold a lot of data, a lot of metrics for us. I don't believe I brought my, no, I didn't include a slide that, I had another slide that talked about the write latency and read latencies that we're observing right now, and they're both within very acceptable limits for us, and so we're happy with the way the system is working. Another one of the important things that motivated us is, of course, we want to be able to get the data out. It had to be pretty simple to us, or pretty simple to consume. The number one thing, as far as that goes, though, is graphs. I showed a picture of the graph earlier. People, it turns out, have this incredibly low tolerance threshold for waiting for things. We're just, by our nature, we don't want to sit around and wait. And when people are waiting for graphs, they lose it, And so that was our main goal there, was to make sure that we can get data points out quickly. And that's what influenced our decision to make it a roll-up system rather than compute the roll-ups on the fly at query time. We get a much better service level, and things just in generally flow a lot more smoothly. Graphs are fast, and people can maintain their composure. Another goal that we were shooting for was to have a multi-tenant system. And this was our own organizational needs. We knew that we were going to have multiple customers within Rackspace, not Rackspace customers, but internal Rackspace users who were going to need to put data into this system. And we also treat each of our Rackspace customers' data as a as a customer as well. And so they all have to be treated the same. But the thing is, some users are going to be big users. They're going to demand a lot of resources, and other users aren't going to demand a lot of resources. And so whenever you start dealing with this kind of problem in multi-tenant environments, things get difficult pretty quick because everyone has a different set of expectations going into it. And it actually turns out to be pretty hard. I think the main reason of this is because when you start dealing with multiple tenants, multiple expectations, you're going to have a different set of metadata or meta requirements. And this is something that just makes, it's the hard part about multi-tenant systems is accommodating everybody. And so we've had to do a couple different things to help accommodate that. And at the far ends of the distribution, there's probably the unhappy group, but I think we've managed to accommodate a pretty big section in the middle. Something else is I like to call Blueflood a lipstick system. We at Cloud Monitoring, our primary concern is making sure that the entity's servers are monitored and that alerting happens when that monitoring or when those servers go down or break. Getting pretty graphs isn't something that's going to be mission critical. It's nice to have, but if this system has hiccups, data is delayed by a minute or something like that, you're not going to have customers, well, your customers screaming at you. You might be screaming at the people running your graphing system, but your customers aren't going to be upset if you're not getting your data points as quickly as you need them. So we knew going into it that it wasn't going to be a mission critical system for Rackspace business. We knew it was just going to be something that was nice to have. And so with that in mind, we wanted it to be a pretty cheap system. We ended up co-opting the Cassandra hardware that we were already using. We realized our Cassandra database cluster was using a lot of disk, but we really weren't using a lot of the CPU. And so with Blueflood, we realized, well, this is going to be a pretty CPU-intensive application. Let's co-locate them on the same boxes. We know that this isn't something that we're going to be able to do forever, and so we didn't go ahead and leverage the locality of the Blueflood instances to the Cassandra instances. So we can separate them, and we're still going to have the same set of constraints as we're working under right now. But that's something that we did think about. Another thing that we wanted to do was avoid Hadoop, and it's not because we hate it. It's just something that's extremely heavyweight. Hadoop brings operational requirements in. It brings hardware requirements in. And again, with the small team that we are, it wasn't something that we wanted to undertake. We like Hadoop. We use Hadoop for our own data warehousing and long-term crunching type things. But it's not something that we wanted to make part of our metric and graphing system. And so those were, that's what motivated us and drove us to create Blueflood. And this is what we ended up with. And I'll spend the rest of the time talking about the different components here, but it starts at the bottom and it works its way up. At the bottom, of course, is Cassandra. And on top of that, there's just some libraries that allow us to get data in and out. There's a little bit of state management. This is all one unit right here. And then there's some tools that allow you to do caching and metadata storage. And at the end of it is, at the top layer, are your query and ingestion APIs. I'm going to go ahead and highlight all of this stuff here you get for free. We ship you that. This stuff here you have to come up with on your own. I'm going to explain why we did that later. We shipped some reference implementations of the API endpoints, but there are some good reasons why you probably want to do things your own way there, and I'll explain those when I get up to that layer. So let's first just talk about the database. We've been using Cassandra at Rackspace for quite a long time. It's been part of the beginning from Cloud Monitoring, and so we still have a 1.0 Cassandra cluster that we use to store our control data. And so that's where we brought a lot of our operational experience from, which motivated us to start developing Blueflood using Cassandra 1. We've made sure it's compatible with the new versions as they've come along. We haven't started working in Cassandra 2 yet, and so although I imagine Blueflood will work fine with Cassandra 2, it's not something that we've had a lot of time to spend testing and making sure. We also, started using CQL very early on. This would have been in the CQL 1.0 timeframe. And at the time, CQL was a very good tool for getting you away from having to deal with Thrift. You know, Thrift, everyone complains about having to set up your queries and actually execute them, and it's something that was involved. You had to do a lot of work. And CQL at the time made that pretty easy because it did make it look like SQL. CQL is, you know, if you were using CQL 1.0 and you look at CQL now, you realize, oh no, you know, this is something that's totally different. CQL has changed more into something that's really good for data modeling, which for us, you know, we knew we were dealing with time series data. We knew that we were going to have pretty long rows. The data modeling part wasn't so important for us, and so we ended up moving to using Astyanax. There we go. And we've been pretty happy with it. I still think it's pretty, as far as a client library goes, it's pretty low on the maturity level as far as software. We noticed that it has a lot of bumps when your network isn't quite so predictable, and the connection pooling especially has a lot of tendency to start going through the connections when there's a little bit of network hiccups. Other than that, we've been pretty happy with it. I know that the future is everything's moving, you know, native and CQL driven, and we plan on being fine with that. But we like we still like to think in terms of very wide roads, which I think CQL 3 makes it pretty hard to do. Another thing is we also experimented early on, and this would be in the Cassandra 1.0 timeframe, with the various different compaction strategies, you know, leveled and size tiered, and we really didn't see much of a difference. And at the time, you know, looking back from here and now, it was obvious that leveled compaction was pretty immature. There's still bugs in there, and as you know, if any of you pay attention to the tickets, they're still actively getting worked on, and I think leveled is getting there. But we've tested with both, and we really don't see much of a difference as far as in terms of read performance. And so use whatever compaction works good for you if you want to use this. Some Cassandra tickets to watch out for is first that could change this would be 5685, and that's the one that sets up TTLs that are per column family. TTLs end up being pretty important in Blueflood because it's just a nice way of getting data out of the system without having to go back and reap it out later. Every customer can have a different TTL for us, though, and so that makes per column family TTLs kind of a non-starter. Doesn't help us. But if you're using Blueflood and you only have one tenant, which is you, then that might be a good thing to use. You can expire entire SS tables at a time. Another one is Cassandra 3974, and this is the one that set up TTL histograms so that the compaction strategy can know whether or not an SS table is a really good candidate to compact. And this will only apply if you're using size-tiered compaction, but this is obviously something that's also good. Cassandra 5228 is one that it tracks the maximum TTL per SS table so that it can just wipe out the whole thing without having to traverse every entry in it. Again, this isn't going to work too well for us the way we have things right now, because within a single SS table we're going to have lots of different TTLs per tenant. But we could make this work, I think, if we wanted to bucket our column families. So this column family would be for TTLs between 0 seconds and 12 hours. We could have another column family for 12 hours to a day, another one from a day to a week, and so on. And so we could bucketize our TTL column families and get away with something like that, and that would make compaction a lot easier. But like I said, in general, we haven't seen a lot of problems with compaction ruining our throughput, ruining our read latency distribution. And so we were actually worried about that at first, but it turns out not to be a problem in actual practice. Now, like I said, we're just ramping up this system, and so things like that may change in the future, and we may need to start thinking about how compaction affects things. But right now, we don't have a problem. Things are working good. I'm going to spend some time now talking about what metrics are, how they get into Blueflood, and some aspects of that. A metric is basic at its most basic, just a one-dimensional signal. It's something that has an ID and a value. Now, in the rest of this presentation, I'll say ID and I'll interchange it with what we call a locator. A locator is something that's used in the Blueflood code base as a concept for a metric ID. It's mostly an opaque string as far as Cassandra and most of Blueflood goes, but the nice thing is that it's a composited key that always will start with the tenant ID of who owns the metric. And anything after that, it's up to you. You can stuff as many things in there as you want. I included an example up here where that's just going to end up being the whole locator and the primary key for your metric, and that's how you find it. You can tell I've put in the name of a host, what we might be monitoring, and then the units of what we're bringing in. So put whatever you want in it, just don't change it because it becomes very permanent. It's your row key for many things. A metric has a type associated with it. It's pretty obvious you're going to be dealing with doubles, longs, and then in our cases we also allow string and Boolean metrics, and those are a little bit different and behave a little bit differently, and I'll talk about those in a bit. Type determines how the metric gets serialized on disk. We do use version serialization so that we can change those things up in the future and also support different, more complex data types in the future. Here's an example. This might be hard to see in the back. Here's an example of what a metric looks like. We use an open source collection tool called Reconfigured. It has a daemon called Node.js that is capable of going out and making remote checks. Basically any kind of TCP check. It can do HTTP, it checks mail headers, not mail headers, it checks mail banners, things like that, SSH banners. Anything that can be checked externally on your server through a TCP port, Node.js has probably got a plugin to do. And so this is a single check that got executed. It's an HTTP check, but it's got 5 metrics in there. One that explains how many bytes came back. In this case, it was a 0, a 32-bit integer. Time to receive the first byte, 64-bit integer. It took 257 milliseconds, and then it goes on. This would end up being 5 separate metrics in Blueflood. It'll get split out. And this is where I talked about, or earlier, where I referred to everyone's ingestion pipeline is going to be a little bit differently. So we let those ingestion APIs be pluggable and replaceable. The interface, as it turns out, is actually pretty simple, and I'll explain more about that at the end. But for us, our ingestion pipeline is we break these up into different metrics and then send them into the system. Metrics sometimes have units. As you can see on that example before, there were no units associated with those metrics. By looking at the metric name, you could figure out, well, this is bytes, or this is milliseconds, or this is whatever. But it wasn't something that was explicitly declared as part of the metric. And so for us, and again, this is part of our ingestion pipeline, we guess on this. For lots of those Node metrics, they are named in a very predictable way to where if you look at the last tuple of the locator, okay, this is obviously bytes, or this is obviously milliseconds, or this is going to be a string. In your own enterprises, you're going to see that this is usually the case. The way your metrics get named, you can guess at what the metric units are going to be. As far as the way the column families are built for Blueflood, there are several different metrics column families where the metrics are actually stored. There's one full resolution table that as the raw metrics are brought in, they're just written straight to there. And then as they age, they get rolled up and kind of conceptually compacted. And we have 5 different granularities. And so there's rollups that happen at 5 minutes, 20 minutes, 60 minutes, 4 hours, and then 1 day. This is how we keep that predictable query time low. In general, the less data points you query, the better, the more predictable distribution of your query latency is going to be. And so we query at coarser granularities to reduce the number of data points returned. The column families each get one row per metric, and the locator is the key. There's no bucketing. One of the constraints that we went into with this system was that the average frequency of a metric was going to be 1 every 30 seconds. Obviously, if your frequency is a lot higher than that, you're going to want to employ some kind of a bucketing. We plan on doing this in the future, and I don't think it's going to be pretty hard. It just changes the way that you resolve, which row your data is actually in. And so we'll get there when we need to get there. It's not going to be a problem, but right now we don't bucket the rows at all. We just have one single long row per metric. There's also a column family that stores the metadata, and this ends up being also 1 row per metric, and it's just a simple key value. This is where we store lots of different things. This is where we'll put the units, things like that. Another table that we have, or column family that we have, is one that stores the rollup state. And I'm starting to use terms like shard that might not make a lot of sense. Shard is a way that we partition the rollup space so that no one single rollup node is responsible for rolling up too much of the data set. And we have to keep track of what has been rolled up and what hasn't been rolled up. And that's what the rollup state's for. We also need to have a way of keeping track of which metrics are actually active, and so we have a column family that does that. And it's got a TTL on it, I think, of like 24 hours. And so whenever a metric comes in, it's basically 1 row per shard, and so it's limited to, in our case, 128 rows. And as a metric comes in, we'll append its locator to that. And so whenever a metric stops coming in, well, it'll disappear out of that row in 24 hours. And so we know, okay, we don't have to roll this up anymore. And that tends to work pretty well in practice. The other nice aspect of that is it limits your rows, and so you can take good advantage of row cache. String and Boolean metrics are special because typically they don't change very often. One of the most common ones that we see is the MySQL version number. People don't update their MySQL servers quite a bit, and so imagine if you were storing a MySQL version string every 30 seconds, just appending another column, you end up wasting quite a bit of space. And so we've added some plumbing so that these only get written to the database when their level changes. There's also some nice things in there to where if it's a little bit of a high frequency metric, that it's kept in memory so that you don't have to always go back to the database to compare. Did it change? Okay, no, don't write anything. There's some good things in there for that. Moving up to the library layers, we just have I guess I'll start with ingestion and then go to rollup and query. These are actually just pretty simple. I wanted to explain the methods that we have. The first method is just obviously insert a list of metrics. Metrics they generally come in together or separate, but we let them bundle up and we write a list of them that ends up resulting in a Cassandra batch operation. There's a method that updates the state. The state is actually a kind of a complicated map of shard to granularity to slot. Now, slot's a term that I haven't used yet, and basically what a slot is a bucket of time. Now, I'll go into some details if I have time at the end about what that is. Rolling up, we need to be able to get the active locators. We need to be able to get that state back that we wrote at ingestion time. And then we also need to get the metrics so that we can run the computations and then store them when we're done. Of course, we update state at the end so we know the rollups actually happened. The nice thing about having things set up in a library like this is it enables us to do some other things that are outside of the Blueflood services. Mainly, we can do bulk load operations and also write some tools that end up being pretty helpful. Rollups, when they are serialized, so when they come in at full resolution, you basically have one data point. And in 5 minutes, at 30-second frequency, you're going to get 10 samples. We store that number, of samples, and then we also keep track of some different components, serialize that into one structure, and it gets written as the rollup. As I mentioned before, serialization is version. Querying, we just have 2 simple methods. We have one getData method that says, get me all the data from this range of time for this granularity. which, if you're not careful, can return a lot of data. And so we've also added another method that says, okay, I just want X number of data points, and it will choose the right granularity for you and then give you back the data points. And that's handy if you're generating a graph. If you look at your average graph, that's 300 pixels or 400 pixels wide, well, you can't really fit 1 million data points in there and have it be usefully presented to anybody. The most you can fit is between 300 and 400 data points. And so that's the sweet spot right there. Moving up, I'm skipping up to the metadata and cache because that's something in Blueflood, we've provided some facilities to have these caches and metadata storage that are backed by Cassandra and have different eviction strategies that are used at ingestion, at query, and even at rollup. But we make them available to users as they write their own ingestion and query endpoints. And so they're integrated and they're all over the place. The first example of one is that TTLs, they're linked to tenants. And well, this is specific to our system. TTLs are linked to tenants. When metrics come into the system, we don't know what the tenant's TTL is. We have to consult a different API. And so we use a cache to keep that around so that we're not constantly hitting this external API to hold that data. You can use the same kind of things on your own. The external API requests, we've created some abstractions there to make these kinds of things pretty simple. Another example is that units, they're usually only very valuable at query time. When metrics are coming into the system, I don't really care that this means bytes. I don't really care that this means milliseconds. And so we don't worry about it too much at query time other than to make that little association, save it to the metadatabase for Blueflood so that it can be used at query time. Rollup scheduling and state management is where the bulk of the guts and logic of Blueflood are. So one of the problems that you have in a system like this is to divide time into buckets without going to a point where you've got this timestamp or whatever that's constantly increasing, which in a time series database usually means you're adding rows or adding columns. We wanted to be able to get time to where we can refer to it in a way that uses a finite set of keys. And the way that we ended up doing that is we've taken time and we've generated our own hashes on that to where time hashes into buckets, and these buckets repeat after 2 weeks. And so if you can imagine a 2-week period that's divided into slots, and each slot is the size of granularity, you have 5-minute slots, 20-minute, et cetera, et cetera. And this repeats every 2 weeks. Well, you're going to have 4,000 5-minute slots, 1,000 20-minute slots, and so on. This page is killing me. I should just quit Chrome. All right, and it just goes on that way. And what this does is this gives us a way of consistently addressing these time ranges because we know it's going to hash to this to this value between 0 and 4031, and so that's useful to us. As time increases, so does the bucket number, the slot, and eventually it wraps back at 0 at 2 weeks. How do we know when something needs to be rolled up? There's 2 different ways. First is whenever an active slot hasn't been updated in a certain amount of time, or it is a certain seconds old. It gets scheduled and then rolled up. There's some logic in there to make sure that we don't do this the wrong way, roll up stuff that's just going to be re-rolled up again later, and things like that. We tolerate late data. It's going to be dependent on your ingestion pipeline. But we tolerate data up to 24 hours late, and we figure if it's 24 hours late, we've probably already forgotten about it and don't care about it so much, and so use a bulk operation or use something else to get that in. Ingestion processors are where you can do quite a bit of customization. This is where you can augment the data as it comes into your system, and typically what you're going to see is data coming in from several different places. At least that's what we see. We have this one generic computing platform, but data comes in from many different places, and so we want to be able to modify this data depending on where it came in from, and so we use the ingestion pipelines for that. Well, one point to point out about that is that the ingestion processors can either be synchronous or asynchronous. And it ends up working out pretty well for us. Now the API endpoints, this is what is, it's up to you. We found that as we started building this and we started accepting data from more places, we had to change our ingestion quite a bit. And so we decided, okay, we're just going to make this completely pluggable. You put your own pipeline in, and things you can respond to these these external changes or these new external data sources without having to modify the rollup scheduler, all the different things that are going on inside Blueflood. And that ends up working out pretty well for us. So modular wins there. We ship with some reference endpoints, UDP and HTTP ingestion, and then also HTTP query. And for us, we use Thrift a lot in our own enterprise, and so we have Thrift endpoints that we use both for ingestion and for query. And if we ever get around to cleaning those up, we'll put those out as a Blueflood module. The only downside to this is it means a little bit more work for you, but the plus side is that we want your pull requests. If you end up using Blueflood and you create endpoints that you think will be useful and general purpose, or even not general purpose, just useful, submit them. We're happy to make them modules or support them in whatever way that we can. The way that Blueflood scales, two places it needs to scale is in ingestion and then rolling up. Ingestion scales linearly by just adding ingestion nodes until Cassandra becomes your bottleneck, at which point you have other kinds of problems. We have 2 ingestion nodes per data center and run them in 2 data centers, and only 1 ingestion node per data center is active, but we do double ingest. And so we can tolerate a data center going away or being partitioned, and still we're getting our metrics into Blueflood. Rollup scale almost horizontally, basically by spreading out the shard ownership. Shards are capped at 128 right now, but it's okay to have multiple nodes processing the same shards. There's a little bit of coordination that happens. Right now we use Zookeeper to do that, but that's a dependency we'd like to see go away, and I think we have some interesting ways of making that happen. Some things that we're working on in the future is local ingestion durability. Right now, when data comes in, as it's being processed, it may not get saved immediately. We're looking at some different ways of making sure that that's durable locally before it gets saved into Cassandra. That helps with restart scenarios and things like that. We're also looking at having a richer metadata API so that when metrics come in, you can associate tags with them and then use those tags as some kind of a facet that will allow you to query for metrics in more interesting ways rather than just by per tenant. And we're experimenting with Elasticsearch and also looking at ways that we can do our own bitmap index to do those kinds of things. And that's something that's ongoing, kind of on the back burner. Also, we're looking at pre-aggregated metrics. Or actually, we're implementing them right now. If you use StatsD or Graphite, you'll know what I'm talking about: counters, timers, those kinds of things. It turns out integrating with StatsD is, well, histograms as well. Deep StatsD and Graphite integration is ongoing. With StatsD, it's hard because they have this concept of things get flushed and the data kind of gets reset to 0. But in Blueflood, the data stays around until it times out. Your counts just continually increase, and most of the time you end up wanting that. Graphite is just involved because of the new rollup types. Integrating with the WhisperDB is kind of involved. Anyway, that's what we're doing to get as far as the future work goes. If you want to get involved with the project, that's where you can find it. It's on GitHub. We have an IRC channel. We have about 3-4 developers in Rackspace that are very active in it, and then some that are coming from outside places who are starting to participate a little more. I'd encourage you to take a look at it. We have a minute or two, a couple minutes for questions. If anyone has questions, I'm happy to answer them.
How big are the rows if you're not bucketing your claim?
Well, do the math. For us, if a metric's coming in once every 30 seconds, you can figure out after a year you're going to have 200,000 rows or 200,000 columns, something like that, which is still very manageable as far as Cassandra goes. Now, if you're having 100 metrics come in a second, well, you've got a different kind of problem. You're going to want to look at some kind of bucketing, and we do plan on having that kind of thing eventually. All right, yes, sir. How do we manage consistency? Right now, I believe that we ingest. I believe that we ingest and read both at quorum. And so, I mean, it's something that isn't configurable, but we ought to make it configurable. It's just that we haven't had a demand yet for that, and so we haven't done it yet. But I can see different enterprises wanting to be able to control consistency. You know, some may want to optimize for writing, and some may want to optimize for reading. And so I can see the utility in that. Great. Thanks for your time.